It's time. All right, welcome to the second day of the TDA week. We'll have two talks today in a morning session, interrupted by a coffee break. And we have a special announcement.
Vanessa Robbins
From the Australian National University in Canberra. And she's going to talk about topological image analysis. Please.
Yes, so this is a rather ambitious and grandiose title, sorry, but it was really just trying to give me the option because I didn't know what I was going to be talking about until much closer to the actual date. Anyway, thank you very much for inviting me to Kyoto, and it's always lovely to visit here. So thanks, Yasu. How do I, there we go, it's not. All right, so I guess this outline slide is really just part of me situating what I'm going to talk about in the grand universe of topological data analysis and so on. And what I will be talking about today is methods that allow us to apply persistent homology to scientific imaging data that's 2- and 3-dimensional. So the reason I'm specifying scientific image data is because in that kind of data, the pixels have very specific resolutions and geometric information contained in them. And so as opposed to, your holiday snap or all sorts of other types of imaging data that goes on out in the world. Okay, scientific image data is usually obtained in a way that is as clean and precise as possible, and we're trying to get some kind of geometric information out of it. So I just wanted to make that point quite clear. And how do we go about turning these digital images into something we can apply persistent homology to? So the first thing we have to do is to create some kind of cell complex, right? Because we need to be able to build a filtration. So I'm going to tell you about the two sensible ways, or two different ways people tend to go about doing this. Once we have our cell complex, we'll take something about the image values and turn that into a function that we will use to define our filtration. And from there, we could just compute persistent homology by adding one little cubical pixel cell at a time. But that, means we're using many, many more cells or cubes than we really need. And so I guess 20 years ago when I started thinking about this, the persistent homology algorithms weren't sufficient to deal with complexes of that size that we were getting out of our scientific images. And so in order to reduce the cell complexes down to something manageable, we used discrete Morse theory to build an abstract chain complex that we could then compute persistence from. All right, so the abstract chain complex is equivalent to the lower star filtration on the cubes, but when we feed the adjacencies in that abstract complex to persistent homology, we're feeding orders of magnitude fewer cells. Okay. So my talk will, once we get that persistent homology, I'm going to tell you a little story about how the difference between these two different ways to build a cubical complex and a type of duality result I obtained with my Women in Computational Topology group. And then the sorts of applications I've been fortunate enough to work on have included porous and granular materials with my group in the Research School of, well, not my group, a much bigger group in the Research School of Physics at ANU. So they run an X-ray CT facility, and a lot of the stuff they image are rocks and bone and granular materials, so hard materials where you can get a decent two-phase segmentation. And then Kate Turner and I supervised a bunch of student projects in the last 5 years or so looking at biometric data. So that's been a bit of fun. And then recently I've started looking at some medical image data with other colleagues. Oh, and that last one, I'm not going to talk about it all today, but I've got quite a fun project going on with Priya Subramanian, who works in dynamical systems and pattern formation, and we're using the same kind of software to study pattern formation. So that's simulated data. Okay, so here's some example pictures. So the X-ray CT facility, my colleagues have really, really amazingly good reconstruction algorithms to turn their so you take 2D X-ray images at many different angles through the sample, and then you have to turn those projected data into 3D voxel space, where each voxel corresponds to the X-ray absorption of the material. Yep. So they've looked at things like, this is a sand packing of sand grains. This one's a metallic foam material. And they look at all sorts of things. So I've had a very long collaboration with that group. The kind of student projects we had fun with were things like fingerprints and trying to cluster images of fingerprints, like from your Touch ID type data. And then retinal scans here, that's also for identification type purposes, these scans. And then this is some of the medical stuff I've started looking at recently. All right, so the basic workflow here is that you get some kind of raw or 3D reconstructed image, and we want to make some kind of geometric quantification. And so we have to process that image in some way to get a representation of the part of the image that we want to be able to quantify. Yeah. And so a lot of this, right, this step here, going from your raw image to your kind of base object, your segmented object here, that is an extremely challenging problem. And I leave that to the image processing experts, okay? So in fact, the most successful segmentation algorithms here are really based on deep learning AI tools now, okay? So I'm not, some people, in the past people, or I even thought about trying to apply persistence to this kind of segmentation problem, but there's so much locally adaptive stuff that you have to do, it's really much better left to the AI tools, right? Cool. So, but once we have this segmented object, we can then think about how we might build a function from that segmented object that will help us to quantify the geometry. Yeah. And so obviously there's many different ways you could build such a function. I think today I will really just focus on the distance transforms to get a so from distance transforms, you get this grayscale function over the image domain. And then we will go through that building a cubical complex and the gradient vector field to compute our Morse chain complex and apply persistent homology. Yeah. Once we have that persistent homology, obviously the downstream analysis is also a huge amount of work and with lots of very interesting techniques going on there. I'm not going to talk about any of that today. What I'm really going to focus on in the next part of my talk is just how do we calculate that persistent homology, and then I will start to talk a bit about some of the interesting things you can do with filtration functions, or some questions around how stable are these functions to perturbations and so on. All right, so we're going to get into some of the details here. So the filtration we're applying is this sublevel set filtration. And so what we're studying is the region of the plane where the function values are less than a threshold. So my threshold is H, and so I look at the structure of this region of space where the value is less than H. So at one threshold here, I'm seeing 3 components maybe, and then as I increase that threshold to include the lighter parts of the image, I will eventually see components joining up, and then at this second last level, I'm seeing, or maybe at the third last level, I'm seeing 2 holes. Oh no, I'm seeing 1 hole here. And then at the second last level, I see 2. That one fills in and this one creates a hole, so on and so forth. Your standard topological change study. And the lesson from Morse theory is that changes in the topology of your lower level sets can only occur at a critical value of the function, right? So minimums correspond to the birth of a connected component. Saddle points locally represent a connection between two local distinct pieces of the sublevel set. And globally, saddle points can represent 2 components merging, or a saddle point can represent the birth of a 1 cycle, all right? And then obviously a maximum is when you cap off the mountain, for example, fill in a cycle, and so we have the death of a degree 1 homology class. So the Morse theoretic picture tells us that we can connect critical points via gradient flow lines. Yep. And so from a saddle point, like this one here, we can flow down to 2 local minima. Sometimes those local minima can end up being the same local minimum. And from a maximum, we can flow downhill to some saddle points, as well as, I mean, obviously we can also flow down to the minima, but in Morse theory, we only want to look at the connections between critical points of index k and those of k minus 1, index k minus 1, okay? And it's this, yeah, I'll talk about this here. So, and then it is this adjacency between the critical points of degree k and k minus 1 that give us the chain complex that we will then filter by the function values for persistent homology, right? So is that's a good picture? Everyone's got that in their head now? Cool. So that's kind of the continuous world picture. And in the continuous world, we have unique gradient flow lines, which is very lovely. But if we want to translate this to the discrete world of digital images and cell complexes, then we have to make quite a radical change in our machinery of what's going on. And in particular, we no longer have unique gradient flow lines. That's just one of the issues that goes on. And I guess we also have the issue that we don't have isolated critical points. So when you increment your sublevel set, even in the neighborhood of a single pixel, you can have more than one topological change happening, okay? So these are some of the challenges that we face when we move from the continuous picture to the discrete one. Okay, but first of all, before we even get to all of that, we have to actually build our cell complex, right? And this is, again, one of the fundamental problems in analyzing digital images. And if we had digital images that were based on hexagonal pixels, our life would be so much easier. Our topological life would be so much easier. But I guess the computational life would be a little bit harder. So we're stuck with our rectangular grids for now, okay? Rectangular grids have this issue of ambiguity about corner adjacent squares. So let me try and explain that a little bit more. Imagine I have this image region where the red B's are the background and the blue F's are the foreground. I now have to decide which pixels I want to consider to be connected to one another, right? So I can either choose my pixels to attach only directly up and down or across, or I'm hearing myself. I'll turn that off. Okay. Or I can decide that my pixels are connected to their corner adjacent cells as well. All right. So direct adjacency is called this 4 neighborhood. When I involve the corners as well, I can call that the indirect adjacency or the 8 neighborhood. So the issue that I'm trying to get to here is that I cannot choose, well, if I choose the same adjacency for both the background and the foreground, I will end up with topological paradoxes. And in essence, the Jordan curve theorem about curves separating regions of the plane, it will fail, okay? So if I chose to, so what I've done here is I've joined the foreground pixels according to the 8 neighborhood, and I've joined the background pixels according to the 4 neighborhood, all right? So you see when I make that choice of complementary adjacencies, then I get a nice little circle of foreground pixels here that surround an isolated background pixel. And so my connected curve here has separated the plane into 2 regions. If I wanted to use the 8 adjacency for the background as well, okay, that would make this little isolated pixel here connect through to its corner adjacent neighbors. And so now I have both foreground and background connecting through each other like this. And so I've no longer, my foreground cycle here no longer separates the plane into 2 distinct components. So that's not desirable from a topological point of view. If I was to connect everything, if I was to connect foreground and background with the 4 neighborhood, I would then lose these blue diagonals and I would have just a whole bunch of isolated pixels that didn't create a curve, and yet, so there'd be this patch of image that just wasn't connected to anything at all. All right. Cool. Yeah, so this is our fundamental problem with cubical grids. And so the way we will resolve this is through building cubical complexes. So the digital topology community, they resolve it by choosing the foreground with 1 adjacency and the background with the other adjacency, 4 versus 8. But because we need to do persistent homology, we're going to build cubical complexes. And so once you build a cubical complex, you will automatically have your sublevel sets connected according to one of these adjacencies. Okay. So here we go. Here are our 2 options for how to build a cubical complex from my digital image. I can either treat my pixels and their values as vertices in a regular grid, and the function values are attached to the vertices here. Or I could imagine each pixel as a little cube, and the function values are now associated with these top dimensional cells. And then I add all the lower dimensional faces as adjacencies between these cubes. Okay. All right, so I can extend, initially I can extend my function values on each cell by taking, in this setting, I take the function value on each cell to be the maximum value of any of its adjacent vertices. So what that means is that in the lower star filtration, I will grow something like this. Okay, so I can only add an edge. So here, when I add pixel value 5, I'm adding 2 edges because the edges have taken the value that is the maximum of their adjacent vertices, right? And then the squares here, the cubes, can only come in at the very last, they only come in at the very last value in the filtration, pixel value 9, because that one's in the center, and so all the cubes take 9 as their value. Okay, in the T construction, we kind of do something that's a bit like the reverse here. We add a pixel and all its faces. So all the faces of a square take the minimum value of their adjacent pixel patches, okay? So if we think about how this connects to digital adjacencies, this V construction, V is for vertex, corresponds to a 4 neighborhood, and the T construction, where T stands for top dimensional cells, that corresponds to your 8 neighborhood. All right. Now observe, homology computations in this little example are extremely different. I will get to that later. Okay. I will return to that later. Oh, this is what I meant. Okay. So now I'm going to do a very quick review of this algorithm process lower star, which is the algorithm that Adrian Shepherd, Peter Wood, and myself came up with many, many years ago. And so this was a method for, I guess, growing our cubical complex one lower star at a time. And we're growing this via simple homotopy expansions, okay? So we add a pair, we have to pair cells with something of codimension 1 greater. Wherever possible, we're going to grow by these simple homotopy expansions, and then we add a critical cell only when absolutely necessary. So in this example here, I'm adding the lower star around pixel value 6. So I always pair pixel 6, I pair the actual vertex with its neighbor that takes the lowest value, and then I grow with these simple homotopy expansions, okay? And those pairings under simple homotopy expansions correspond to arrows in a discrete gradient vector field. And so once we have this discrete gradient vector field, we can apply Foreman's discrete Morse theory to calculate our abstract chain complex and feed that to persistent homology. Okay. So I'm just going to show you this 3D example, which I'll talk you through the 3D example because some people find this a bit hard to pass. Anyway, so you have to imagine what I've done now is I've taken, I'm focusing on the pixel 8 and I'm adding its lower star. Okay, so I'm going to add the lower star to pixel 8. And so the very first sketch here is showing you what that lower star is and the pixels in its, or the vertices in its lower link. Yeah, is that clear? So when I add vertex with value 8, I'm going to pair it to its minimal neighbor. Once I've paired it to its minimal neighbor, I'm left with kind of these 3 faces of a cube. So there's no simple homotopy expansion available to me now, okay? There's no pairs with a free face available. So I have to add a critical cell. So I'm going to add this edge here as a critical cell in that discrete Morse picture. And once I've added that critical cell, I can now start to grow in my simple homotopy pairs again. Okay, so I can pair this edge into that square and so on. And then I'm left at the end with this square that can't be paired with anything within the lower star. Yeah, so now I add a two-dimensional patch here. And this, I guess, is just illustrating something I mentioned earlier, which was that within a single lower star, you can have more than one topological change. And those topological changes can, in fact, be of different homology degrees. Yeah, so if we come back here and think about, in a more continuous picture about what we're seeing here, we're seeing that in the lower link, I had a cycle and a vertex that was not connected to the cycle in the lower link. And so I know that I'm going to have an index 1 change to represent the local new connection that is being made. And I'm also going to have an index 2 change to represent the filling in of that cycle. Okay, and so that's exactly what we found at the end here. We had an index 1 critical cell and an index 2 critical cell. Okay. And this index 2 critical cell isn't quite where you might think it should be. I guess if I was going to draw by hand and sketch out what the topological change really should look like, I might want to make that edge here between 8 and 1. I might want to make that one critical. Okay. But my point is that it doesn't matter too much in terms of the local homology computation, and as you get the correct you get the correct dimensions of critical cells even when maybe you make not the optimal choice. Okay, so this, yeah, there may be all sorts of other issues associated with that choice, but at least locally it's reflecting the true change in topology. Okay, so once we have these gradient vector fields, we can do much more than just calculate homology, because we can use them to, I guess, do some image processing of some sort. Okay, so with this gradient vector field picture, we were able to come up with an algorithm that could give us topologically consistent skeletonization and partitioning. All right, so this was a whole, all right, before this algorithm, people could construct partitioning of regions in digital images, and they could construct skeletons, but they could not guarantee that the skeleton was topologically dual to the partitioning. Yeah, and so this topological point of view and using gradient vector fields, I think, gave us a very lovely solution to that problem. Gradient vector fields also allow you to simplify things. So I haven't put in a copy of the initial gradient vector field, but if I just follow process lower star without any simplification, then I have a much more complicated set of critical points and adjacencies between them. But we tend to follow this process of which we call close pair cancellation. So close pair cancellation means that my two critical cells are they're adjacent under gradient flow by a unique gradient flow line. That's the criterion we need to be able to cancel, to be able to reverse the gradient flow line without introducing any cycles. And then the close pair concept is something that Marian Roszek might talk a bit more about, because I know he's been thinking about similar ideas recently. But the idea of close pairs is that so I've got a cell of index k and another cell of index k minus 1 that are joined by a gradient flow line. Okay, so if I look at my K-1 cell, it could be joined by flow lines to other K-dimensional cells, yeah? So I want all those other K-dimensional cells to be higher than the one I'm going to cancel with, yeah? And similarly, for the K-dimensional cell, it may be connected to other K-1 dimensional cells, and I want all the other K-1 dimensional cells to be much lower than the one I'm going to cancel with, okay? Yep. Yep, yep, yep. I didn't put that in my explanation, sorry. Yeah, so the black dots are local minima, and the cyan dots are saddle points, index 1 saddle points. There are gray dots, which are local maxima. Yeah. Yep, so that would be a local maximum, saddle point, minimum. Yeah. Oh yeah, and so this picture is really obtained from analyzing the gradient vector field, right? So the colors are pixels, all of which, if I follow gradient lines from all those pixels, I will end up at one particular local minimum. Yep, is that clear? And then the difference between the white lines and the cyan lines here, the difference between the white and the cyan lines that are coming out of the saddles. So the white lines are descending gradient flow lines from a saddle point down to a local minimum. Yep. And I'm only plotting the ones that are where the saddle point value is below a particular threshold. Yep. So the color stuff represents pore space, and the gray stuff represents the solid. And so the definition of more skeleton here is that I keep the critical points whose values are below some threshold that I choose, and then I plot their descending gradient parts. Yeah. What else do you want to say? Oh, I guess I would just like to say that Diamos is still going strong because it was written by Olaf, and he's amazing. And I think so Diamos is still working, even whatever it is, like 10 years later, and it's still fast. And I think I hope I've recently uploaded Jupyter Notebooks into GitHub so that you can actually, with some examples of how to interact with Python. If anyone loves writing Python bindings for C++ code, can they contact me? Because I tried and failed miserably. So I did want to update it, but it was way beyond my programming skill set. So for now, you have to do a little exit call to execute the C++ bit, but at least there's some Python code to help you interact with the C++ stuff. Okay. Cool. So now we're going to come back to this question of V construction versus T construction. And how am I going for time? I have no idea what the time is. Gosh, I thought I had so much time on my hands, but I did not. Okay, so what's going on here is that I guess this little study arose because my Women in Computational Topology group met in 2019, and Adelie, I think it was Adelie, said, I really want to be able to use your skeletonization stuff, but you're using pixels as vertices and I want my pixels to be the cubes. So how can I make that work? And that led us down this really interesting theoretical direction to understand exactly what was going on and what the relationship between these two things are. Yes, so the next bit of the talk will help to explain, I hope, why these things are so different and how we can establish a method for actually converting between them in a nice and easy way. So the idea is that if I have software that does persistent homology with the V construction, but I really want it to give me answers for the T construction, I have a method now that will let me use that V construction software and then convert the output into the T version. Yep. Awesome. Cool. So at its heart, we have to define this notion of when two things are combinatorially dual. Okay, so this is basically formalizing the picture that you would get from a Delaunay versus Voronoi partition picture, where your Delaunay triangles are geometrically dual to your Voronoi vertices. Yep. So you can think about the Voronoi cells as partitioning the plane in one way and the Delaunay triangulation partitioning the plane in another way. And they are combinatorially dual in the sense that every triangle corresponds to a vertex in the Voronoi. For every edge, there's a dual edge. And for every Voronoi face patch here, I have a corresponding Delaunay vertex. Yep. So we're going to build something similar with our cubes. And we are going to filter that. When we filter these things, right, we want the filtration to be a simplex-wise filtration, right? So I really have every single cell ordered in a prescribed fashion that is compatible with my function f. And then in the dual construction, I have another function g, and it's the reverse ordering on the dual cells that's compatible with this function g. Yep. Cool. Okay, so if I look at applying that kind of idea to my T and V constructions, I very quickly see that the V construction is building a complex that's significantly smaller than the T construction, yeah? And so how should I make, I guess we've got all these extra vertices around the edge of my T construction. What are the dual patches, okay, in the V partitioning? That's the question. And in order to obtain something dual to those, I have to pad my image, all right? So here's my initial set of function values on a grid. I have to pad my image out by adding a whole lot of extra cells around the boundary, extra pixels around the boundary, and those extra pixels turn into extra cells here in the V construction. Yeah. So this number n is going to be, I kind of want it to be infinity, but I kind of don't want it to be infinity. I just want it to be a really, really big number that is outside the maximum of the function values here. Okay. And then I can't really talk about a strict duality for just a single patch in the plane here. What I need to do is to, because my plane is unbounded, I have to turn this into a compact manifold. And so I'm going to do that by taking everything around the boundary and identifying that boundary to a single point. Okay. And then what we're able to show is that if I have this T construction here, and I imagine, so I'll try and decipher this. This was a notational nightmare, this thing. But what I've got here is my T construction applied to my image pixels. And here I'm adding a single D-dimensional cell attached to the boundary of the T domain, okay? So I'm taking my blue region here, and I'm just imagining everything outside the blue region to be one big cell. Yep. And then the t hat refers to the function values that I assign, right? So that big cell that I've attached, I'm giving that cell a function value of infinity. Now on the V construction here, I've had to pad it. So this is my padded image. And then with my padded image, I'm now going to take all these cells on the boundary here and identify them to a point. Okay, so that's a different operation. Here I was capping, here I'm identifying things to a point, and the function value I'm going to use to filter this thing is going to be the negative of the image values, okay? Because I need to be able to reverse the ordering of the cells, right? And so now, when I do this, when I build these two filtrations, I have dual filtered cell complexes, and I guess that's the result. They really are dual in this nice sense that we defined, okay? Okay, and now we want to interpret what's going on in terms of the persistent homology here. Okay, so in terms of the persistent homology, the act of padding and adding a d-dimensional cell, the capping, so padding and capping doesn't change my persistence diagram at all. But this act of compactifying the boundary to a single point and then filtering using negative function values, that really does change the persistence diagram, okay? And it changes it in a way that you can see quite clearly here, which is that I'm going to, by identifying the boundary to a point, I'm basically removing this d-1 cycle that existed from my negative n values, right? So remember, n was a very, very big number. So when I make it negative, it's a very, very big negative number. So this padded V image will always have start with a 1 cycle, I guess, is going to be its starting point, that value minus n, and that d-1 cycle will only ever die when I reach the maximum image value. Yeah. So that one gets removed when I do this quotient operation, and it is replaced with a d cycle, which is representing the d sphere. Okay, and that d cycle is created when I fill the final maximal pixel value, and it lives to infinity, right? Cool. So this result is now summarizing how the pairs in the persistent homology diagram, how they really change from one version to the other. Okay, so this is saying if I calculate things using the V construction, then my T persistence diagram will look like this. Okay, so I take the negative values and I change their dimension. Yep. But I have to remove that extra cycle and then add in the new persistent homology class. Yep. So this part of the result, the switching from PQ to -Q minus P in a different dimension, that is a result that is adapted from much earlier work by Herbert and others, and then also the Vin de Silva, Morozov, Vedamo Johansson paper. So these are two very nice papers which helped us understand that result. I guess the difference is that we've got different cell complexes that we're filtering, so it's just a slightly different technicality underlying it. So this is now the same theorem, but getting the V diagram given a T construction. So here I'm illustrating it for you in terms of that. Now I start my T construction with a -1 cycle and I grow it like this, okay? So now we see that by adding in that extra -n padding, that's what helps me resolve the ambiguity between the T construction and the V construction, right? So now we see that the intervals for our persistent homology are nicely dual to those that we had using the V construction. Yep. Cool. I'm pretty much done, aren't I? Anyway, that's okay. I will skip through this. So yes, what I wanted to talk about now was to do with the building this filtration function. Yes, okay, so sign distance transforms. That's what we're doing here. So we had a segmented image, and I want to characterize that segmented image geometrically. And so the favorite tool in my porous and granular materials group was to build something called the sign Euclidean distance transform, right? So sign Euclidean distance transform means I really approximate the Euclidean distance from each pixel to the boundary with the other phase. And then I make the distances negative in one phase and positive in the other, right? And so when I do a lower star filtration on this distance transform, I get a really nice summary of both the geometric features in the pore space and also in the grain phase, the solid phase, okay? So it's a very nice tool, but how stable is it, right? So there were two quite practical questions that my collaborators were always interested in, to do with how does persistent homology change if we change the resolution of the voxels that we've used in our image acquisition and so on, and how sensitive is that distance transform to changes in segmentation, right? Because my first step is to segment, and we all know that segmentation algorithms are a bit unreliable, right? So how robust is that distance transform with respect to segmentation? Okay, so these questions I also explored with my Women in Computational Topology group, and basically we can establish the change with image resolution just using standard bottleneck stability. And because I guess particularly distance transforms, we know are Lipschitz with Lipschitz constant 1, and so we can get quite a nice bound there, right, on the change in homology with different pixel spacings are, okay? And then how sensitive is that distance transform to changes in the segmentation? We had to build a model of what that process was of segmenting and then computing a distance transform. So that model I will describe here. So I guess the fundamental problem is that each pixel or voxel here represents. So in the initial X-ray CT imaging, each voxel is representing the X-ray density of the material in a piece of space. Yep. And if I've got if my object that I'm imaging consists of two materials, one of which is solid and one of which is air, and assuming that solid has a single X-ray density, we can say that each voxel is now the value in that voxel from my X-ray data. That value is proportional to the density of the solid in that voxel region. Yep. And so this is my model here that X, that's my model here, rho. So rho at resolution R and location X is the volume fraction of my solid object in that voxel. And then my digital approximation to this ground truth object is going to be a threshold on that density function, okay? And now we face the problem of there is never, ever going to be a single threshold that captures something well, if my resolution, if there's parts of the object that are below the resolution of my voxels, then a single threshold can never give me an accurate representation of X, right? That's just a fundamental problem. And that is exactly why AI algorithms are better at doing segmentation than any kind of thresholding operation. But we're just going to explore how bad can it get, okay? And we did that using something. We did, Teresa Heiss really led this analysis, and we derived some really nice bounds based on assumptions about the geometry of the object in terms of its reach. And this thing called the leash length, where S here is going to represent something about the pixel resolution. Cool. And in terms of the pictures here, suppose this was my ground truth. So this ground truth picture is supposed to capture this idea of microporosity. So there's a fundamental problem in these porous materials that there will be structure there is always going to be structure at length scales below what the physicist can image, and that can potentially carry important information. So if I had this as my ground truth with some microporosity in there, then my distance transform would look like this. But if I now threshold and apply a distance transform, it looks very different, right? So my error can really be very significant. Okay. And this is illustrating the bottleneck distances between persistence diagrams at different resolutions. So this number down here is telling you how many pixels are in the image. So I start out with a probably 250, I don't know, I'm starting out with a nice high resolution version of my image here. And then I'm subsampling, I think I'm just decimating by 2. So I'm going from whatever that is, 2000 and something, down to 1000 and something in one jump. Yep. And then 512 and so on and so forth. And so the green dots are giving me the leash bound, and the red line here is giving me that density bound. So you can see the leash bound gives a really dramatic overestimate at the lower resolutions here, whereas the density bound we obtain gives you a much closer upper bound. But at the higher resolutions, it's the other way around. Yep, so there's not one, it's not a simple relationship there on the bounds. So you can read about more. If you want to look at that in more detail, you can look at our paper. And I'm sorry I went so long. I really thought I had a very short talk, so I went too slowly at the beginning. Are those small dots a bug or a feature? The eternal question. Clearly here, they are a bug, whereas before they might have been a feature. But you can, I guess my point here is you can build some clever little filtration functions to get rid of those dots using that distance to measure idea. So I guess but once you start introducing things like that, you've now got lots of parameters to play with. But if I do clean up those dots using this distance to measure idea, I get a much nicer distance transform here, for example. Cool. So I just want to point out that there's heaps and heaps of work in applying persistent homology to digital images, and I have not mentioned any of it. So I encourage you to look further afield. I guess my takeaway messages were that when we were looking at porous materials, there's always going to be sub-resolution structure, and that will always confound your accurate geometric measurements. But at least now we have some error bounds on what they are. And a lot of my current applied projects are focusing a bit more on how to design nice filtration functions to give us something that captures the data in a way that will be useful to the scientists. So that's the really fun part of applied work, right? Is working with the application domain and adapting your methods so that they do something good. Yeah, and huge thanks to all my co-authors below who have contributed in one way or another to the work I presented today. Thank you.